These are the notes for Unit 8, Day 2, and they start on page 6 of your packets. With these notes, we're going to look at relating motion to integration, and we did this first semester with respect to differentiation. So now we're going to look at it with respect to integration. And so our central question is, how do integrals explain characteristics of motion? So if you remember back to last semester when we related motion to differentiation, it was very vocabulary and intensive, and today is going to be along those same lines. We're going to have a lot of vocabulary here that's going to kind of guide our process. So let's kind of frame it in this respect. We have an object, has position x of t, has velocity v of t, and acceleration a of t. So those are the functions we're going to kind of define as position, velocity, and acceleration. So when we were talking about differentiation, we defined things like the velocity, the instantaneous velocity is the first derivative of position with respect to time. Well, knowing what we know now about integration, we realize that we can separate these variables, right? So multiply by dt. Velocity is a function of time. That function is time dependent. There is no x. There's no x variable to relocate. So we quite simply then integrate this. And if we integrate this, that we would call that in the last unit solving that differential equation, right? Because this is just basically a differential equation. So we can look at motion with respect to integration instead of differentiation. So when we look at this, we're saying if we integrate the velocity function with respect to time, we get that is equal to integrating 1 with respect to variable x. So what does that mean? Well, that means the change in our x position. So we know that integration, if we go back to Unit 6, represents a change in a value. And so this represents our change in position, which is what we call displacement. And then we can look at acceleration. We know that from differentiation, acceleration was the first derivative of velocity, also the second derivative of position. And likewise, with integration, we can separate the variables and integrate. And so we have then that when we integrate the acceleration function with respect to time, we get our change in velocity. So we're going to stick with these two and define those as displacement and the change in velocity. So our displacement then we know is this. So we know that integration is a change in a value. So integrating the velocity function with respect to time is if we have a starting point and an ending point, if we have a definite integral, right? These are just antiderivatives up here. They have no upper and lower bound. If we start at A and go to B, we know that those two times, then we know that we have found the displacement of the object. So we also can express displacement as the final position minus the initial position, and this is the antiderivative of 1 dx. And our change in velocity then is integrating the acceleration function through that same time interval. And that represents the change in velocity. So this is going to represent this integration, which is the velocity at B minus the velocity at time A. So we're going to really rely on these. And if you notice, looking at these expressions, these expressions look a whole lot like the fundamental theorem of calculus part 1. So that really ties into these applications as well. So we have a separation of variables situation to set up these definitions, and then we can call this an application of the fundamental theorem of calculus, part 1, that evaluation part. So let's go through the definitions then. We know that we have displacement, the net change of the regions between the function and the horizontal axis, and so we know that displacement is integrating the velocity function with respect to time. If we want to talk about total distance traveled, then it's like treating all regions between the function and the horizontal axis as positive in value. And so when we have those regions on the velocity graph, we've we've considered all of those to be positive. And the way we express that is using the absolute value. And that's we did that when dealing with derivatives too. And so when we talk about total distance, a lot of times the total distance concept is really kind of a calculator-based concept because it's because of the absolute value function that you have to work with. And we'll talk more about that when we get to an example dealing with total distance. Okay, so let's take a look at the fundamental theorem of calculus part 1. Right, so we have, this is our fundamental theorem of calculus. I brought that back from unit 6. And so you notice how similar this looks to our displacement and velocity definitions. If we had v of t here, then this would be x of b minus x of a. If we had a of t here, then this would be v of b minus b of a. So that's the tie back to the fundamental theorem of calculus. And so if we relate this back to displacement, then this is integrating the velocity function. So this derivative becomes velocity function, right? Velocity is a rate of change. And so that would be in the integrand. And this would be xb minus xa. And if I added xa to both sides, then I could solve for xb. And I get the displacement plus the initial position. So if you think about this just conceptually, right? Our final position is where we started and then plus however we moved. So that movement could be positive, that movement could be negative. And so if you kind of think about this conceptually, it kind of helps set up the rearranging of the fundamental theorem of calculus part 1. So when we're looking for setting this up, we're looking at starting at time A, which then is represented here in this starting position. And then we end at time B, which is represented here at that final position that we're solving for. And then I want to bring back 2 concepts that we talked about in day 1, average velocity. But we can approach it now in 2 different ways. So we can approach it finding the average velocity given a velocity function. So we're literally finding the average of something we have, right? And we know that that is an average value question that we just learned in day 1. But we can also go back to differentiation and know that our average velocity given the position function is our algebra slope. So we're still going to talk about these 2 concepts too. Finding those average velocity values being dependent upon the information that we're given. Okay, so that kind of summarizes all of the, like I said, this is very vocabulary intensive, but that kind of summarizes all of the vocabulary that we need. So let's take a look at an example. We've got a particle moves along the x-axis so that at any time t greater than or equal to 0, its acceleration is minus 4 sine 2t. And then it gives us some initial positions here. If the velocity at t equals 0 is 7, and its position at t equals 0 is 0, then find its position function as a function of time. So what we have to recognize is that this is an application where we have an acceleration function, and it's asking us about position. But we don't have anything defined. You look back on the previous page, right? We don't have anything defined to get us from acceleration to position in 1 step. So we got to kind of 2-step this. So the first thing we're going to do is use our acceleration functions to get us a velocity function. So we are quite literally doing solving a differential equation for a particular solution. Okay, we don't have the upper or lower bounds. All we have is a starting position. So we're going to look at this to find a velocity function. So to do that, we're going to kind of rearrange this. And then we can go ahead and say integrating 1 dv is the same as finding our velocity function. If we had an a and a b for our lower and our upper bounds, then we could have vb minus va, but we don't. We have an antiderivative here. Okay, and then we're going to integrate this. So we're going to integrate the acceleration function, which is negative 4 sine 2t. Okay, so integrating this, we know we can pull the 4 out, and then the antiderivative of sine of 2t is minus cosine 2t, so the minus sign goes away, and then divided by 2, right? Divided by the derivative. This is a place where they're sneaking in that reversal of the chain rule, or u sub, if you want to call it, and then we have our plus c on the end. Okay, so we need this initial condition, v of 0 equals 7. So I'm going to simplify this, and I'm going to put that initial condition in. Okay, so when time is 0, v is 7. So 7 equals 2 cosine 0 plus c. Cosine 0, that's the 0 radians is the right side of the unit circle. Cosine is the x coordinate. So this is 1. So we have 7 equals 2 plus c. So we know c equals 5. So we can come back to this step right here and put 5 in for the constant of integration. And now we have our particular solution for velocity. So we're halfway there. We've got our particular solution for velocity. We're going to use this and integrate for the position function. But let's just pause here for a second and scan. And maybe you can pick up the answer already. And if you can, great. Go ahead and circle the answer you think it might be. We're going to go on, though, just to complete this process here. So let's find the position function. So we're going to integrate the velocity function. The velocity function is 2 cosine 2t plus 5. So let's go ahead and integrate this. So we have the antiderivative of cosine 2t is sine 2t, and then we have to divide by 2. That's that chain rule. Notice the chain rule is repeated every time, right? Because that function never changes. And then we have to integrate this. This is 5t plus c. I'm going to simplify this by canceling the 2's. And we can just pause here. You might be able to see the answer now. It's a multiple choice. So when you see the answer, you stop the solution and you move on. So if you saw it back here with the velocity function, that's great. These are your notes, so you might want to put these steps down anyway. But let's go ahead and plug in the initial condition, 0, 0 for t's. And when we put in 0 for t's and 0 for the x position, then the c is 0. And so we just end up with this function. And so we know the answer is A. Okay, so this was a multiple choice question. This is a free response question, but it's the same question. Particle moves along a straight line. These are really common questions to have you solve these in a kind of in a differential equation sort of style. Right, these are just particular solutions for differential equations. So this is really a Unit 7 question, but it's dealing with motion. Okay, so why don't you pause the video and try this one on your own and see if you can come up with the position function. And then this question is asking what is your position at 6 seconds. So we talked about using a differential equation to find a final value, right? Back in Unit 7. So this is that type of question. Okay, if you're coming back now, I'm assuming that you've attempted the solution here. So let's go through it. So we know that we're going to be integrating the acceleration function to find a velocity particular solution. So I'm going to switch that just to make it look a little nicer. And the antiderivative of 1 dv is the velocity function itself. And then we're integrating for t dt. So that's 4 times, and then let's do the reversal of the power rule, bump up the power to 2, divide by the new power, put our plus c on the end. We're going to go ahead and simplify that, call it 2t squared. And then we're going to go ahead and plug in our initial condition. So when t is 0, velocity is -2. And when I plug that in and do the math, we get a constant of integration of -2. Okay, so we know this particular solution here is v of t equals 2t squared minus 2. Okay, so I've got the particular solution for velocity. I don't need to do anything with that because it's asking me for my final position. So I'm just going to go ahead and go right into the next integration process. So, taking this and calling it integral dx equals integral v of t dt. I've already integrated the integral dx, the left side. And so we're integrating the particular solution for velocity, which is t squared, 2t squared, excuse me, minus 2. And so bumping up the power here, these are just reversals of power rules. So t cubed divided by 3 minus 2t plus c. Not much simplification there because we can't do any canceling. So we'll go with the initial condition here. When t is 3, our position is 0. So think about that. T is 3, position is 0. We usually see that the other way around, right? So in other words, we're back at the origin, at the starting point, so to speak, at 3 seconds. So our final position is 0, and this is 3. And so 3 cubed divided by 3 minus 2 times 3 plus c. So doing the computation here, 3 cubed is 27, divided by 3 is 9, times 2 is 18. So we have 18 minus 6, looks like. And so our c then, if this is 12, bring it to the other side, our c is negative 12. So we'll put that back up in here. So there is our particular solution. Still not done, right? We need s of 6. So when we plug a 6 in here, I know I didn't show any of the work, but when we plug a 6 in here, we get 120. So that's our final position at 6 seconds. Okay, so let's just do a quick matching here now that we've gone through a lot of vocabulary. So a particle moves along the x-axis, so that time t, its position is given by s of t. So we're a little variable change here. They often use s instead of x. And velocity is given by v of t. Match expressions with their verbal statements. So go ahead and pause the video and try this matching activity. Okay, if you're tuning in, I'm assuming you're checking your own work. So let's see here, the position of the particle at t equals 8. So this is a final position. So this is going to look like an integral plus x initial. So that's got to be that one, integral plus x initial. So in other words, the final position is 8. We see that by the upper bound here. The initial position must be 1. Okay, change in position between t equals 1 and t equals 8. So change in position we know is just an integral statement by itself. And so we know that the change in position is integrating under the velocity function. And we're not being asked for total distance, so that's got to be without the absolute value signs. So between 1 and 8, notice we're evaluating between 1 and 8. And then total distance traveled, once we see that phrase total distance traveled, we know we're looking for absolute value signs. And I have a typo here. That should be from 1 to 8. I'm sorry about that. That should be a 1 there. And of course, that's this one here. Okay, so that's just, like I said, a little matching for the vocabulary. All right, let's take a look at this example. Learning to work with the vocabulary. So a particle moves along the x-axis. The velocity of the particle at time t is given by v of t. Its acceleration is given by the function a of t. Which of the following gives the average velocity of particle from 0 to 8 seconds? All right, so again, learning to work with the vocabulary. We're being asked for average velocity. We know that we can express the average velocity, since velocity is a rate, we can express it 2 ways. If we're, so we have to kind of think about this. Do we have average velocity expressed as a position or expressed as a velocity? So in other words, am I being asked to average the same function I'm given? Or am I being asked to find an algebraic average rate of change based on something different, based on a different function, based on position? So scanning our options here, I see that there are no options that list position. So we know that we can rule that out. There are no expressions for position. So we're looking for an expression with velocity. So we're being asked to average the function that we have. So which one is those expressions that to average the function that we have? Well, we know that this as an absolute value, we only have absolute value for total distance traveled. So we can rule that out. We know that we have nothing that looks like this with acceleration. So we can rule that out. So we're looking for an average value, and we know an average value is dividing by the domain. And our domain here is from 0 to 8. So it's got to be this one. Okay, so we're given velocity, we're finding its average. It's an average value. Oh, and I have the wrong one circled. That's terrible. So sorry about that. And it should be that one. There we go. There we go. And it should be that one, right? Our domain is from 0 to 8. And so we have an average value of velocity, which means we're averaging the function that we're given. So a couple of these things, this is out because 2 is not the appropriate domain. And likewise here, it looks like they're just trying to do like a algebraic average, like averaging 2 scores on a test or something like that. Okay, so the last one, we're kind of bringing it all together here. We're applying concepts kind of across the board here. And this one, looking at these functions, you could integrate these by hand, but we're going to use a graphing calculator instead. So we have a time interval from 0 to 6, particles moving along the x-axis. That's a really common phrase. It just means it's linear motion. The particle's position x of t is not explicitly given, so we don't have an x of t function. And they don't expect you to find one either. The velocity of the particle is given by v of t equals 2 sine e to the t over 4 plus 1. The acceleration is given by a of t equals half e to the t over 4 cosine e to the t over 4. And our initial position is 2. It says find the average velocity of the particle. Okay, so in that 6-second interval, I'm assuming it's seconds. So we have a velocity function, and we're being asked to find the average of that function. So we don't have a position function. We can't do an average rate of change, which would work out to the same value. But instead, they're saying, hey, given the velocity function, find its average. So looking at that, what they're saying then is we have this domain. And so we have, remember, this is our average value definition, right? We're just writing it a little bit differently. We could, instead of the fraction out front, we could say divided by 6. So our average value is 1/6, and then integrating the velocity function. So let's go ahead and do that on a calculator. We can do this all in one step. Let me just make this smaller so I can see this. At least to put it in, then I'll make that screen bigger. Okay, so I'm just going to call that 1 divided by 6 times, clear that out. Let's use brackets. 1 divided by 6. I don't think I need them, but it's always safe to use them. Math 9. Okay, we're going to go from 0 to 6. I know it's a little bit tiny, but I'll make it bigger before I hit enter so that we can kind of check it over. Actually, I can do this. Can make that shorter. Oh, I can make that shorter, and I can make this a little bit wider. There we go. Okay, so we've got, now I can't see my calculator real well, but if we look at the mode, we're in radian mode, so that's good. Just gonna get back to the integrand location now. There we go. Okay, 2 sine e to the, so e to the t over 4. Now, our variable on our calculator is x, so we're going to put x divided by 4. And then dx, that's our variable of integration. And so when we hit, I'm just checking this over. Oops, see, I made a mistake. I forgot the +1. Not there. There we go. +1. There we go. Always good to check it over before you hit enter. All right, so we get 2 sine e to the pi over 4, e to the x over 4 +1, and times the 6th. So that should get us our answer. And that gets us an answer of negative 0.0816. And that's a different answer. Interesting. Huh, wonder why. Okay, I figured out why this is the wrong answer. So I'm just going to leave this in the video because actually it's a really good thing to talk about. Look at where I put the +1. I put it inside the sine function. And the +1 is outside the sine function. So I got to get this +1 right here, right? I can't have it. I'm taking the sine of that and I don't want to. So I'm going to do a second entry to get that whole thing back. So it's kind of a decent error to leave in the video here. And I am going to delete the plus and delete the 1. Come here. That's where I want the +1. You see how the +1 is outside that trig function? And I'm going to do second insert +1. Hit enter. There we go. 1.949. So it, you know, I mentioned it. I wasn't careful enough, obviously. Wasn't careful enough. I checked this over and I missed this. So I put it in its correct location. And I got the answer now. All right, we're going to keep that calculator active because we're going to use it on part B as well. Find the total distance traveled by the particle from t equals 0 to t equals 6. Okay, so total distance traveled. So it's looking for integrating that velocity function with an absolute value around that. And that's what makes the graphing calculator so powerful. So I'm actually going to do, we can actually do all that right on the calculator. So I'm going to make the calculator bigger so that I can see the buttons better. Okay, so it's a math 9. That gets us our integration. We're going from 0 to 6. And then in here, I need an absolute value function, and that's under the math key. And it's under number right here. And here it is, it's first option, absolute value. And now I have my absolute value. So now I can put in my velocity function. So 2 sine. Now, if you're using the velocity function a lot, you also could put the velocity function in y1 and just grab the variable y1. And that makes it go a little quicker, just so you know. And if you want me to show you how to do that, just ask me in class. Okay, what am I? 2 sine e, so I need e to the x divided by 4. And then I got to close that bracket and put the +1 in the correct location. So now I have, and then let me put the variable of integration here before I start talking about what I have. Okay, so I have the velocity function. I have my absolute values on the outside of the whole velocity function. And I hit enter. It's going to take a little while because the absolute value is a little cumbersome. And it's 12.573. So that is my answer, 12.573. Let's talk a little bit about decimal places because we know we need 3 decimal places. And so the College Board, when they correct this, they would correct this as 12.573. That would be the correct answer. But if you continue to have 26231, that would be okay. You can list as many digits as you want as long as they're correct. They're only going to read up to 5.73. Okay, or 5.573. They're only going to read up to the 3, and they're not going to read anything else after that. Okay. And then let's look at part C. It says for 0 to 6, the particle changes direction exactly once. Find the position of the particle at that time. So we know that changes direction means a velocity of 0 and a sign change, right? We got to go from going away to coming towards. It's going to go from positive to negative or negative to positive. So let's go ahead and graph this. So we're going to graph, I got to look at that function again. Okay, so we're going to graph 2 sine e to the t over 4, so x divided by 4, and close that bracket, +1. Okay, so there's the function. Now the other thing I'm going to do is I'm going to restrict my domain from 0 to 6. So that means restrict my window. X is 0 and x max is 6. That way I'm only looking at what I should be looking at. And I'm not, you know, trig functions oscillate, so we don't want to look at too much. Okay, so let's graph this. Okay, well, I can't see the whole thing, and it looks like I should be 2 plus 1. Maybe I should be up at 3. So we know it doesn't cross again though, so we wouldn't really need to change it. We know it crosses right here. But I am going to go back and change it to a y max of maybe 3.5 or 4, just so that I can see the whole thing. Okay, so we know we cross right here. So at this location, our velocity is 0 because this is our velocity function, and that's the value 0. We go from positive to negative. So we have a positive velocity to a negative velocity. That means we have a relative max on our position function. Remember those type of conversations? So I need that point here. So I have to calculate it. I can't just trace it. Tracing is not going to get me close enough to get points. So let me just show you why that's the case. Okay, so I'm going to turn on my trace, and I'm going to just try to get as close as possible. Let's say there. Notice, some people might take this 5.181818, right? But look at my y. My y is not 0. That's why tracing doesn't work. Okay, so what we need to do is we need to second calc a 0. That's what we need to find. Our left bound, I backed up, right? I backed up a couple spots. My left bound is going to be left of that crossing point. So I'm going to hit enter to confirm my left bound. My right bound, I'm going to click over to the right to get on the other side of that crossing point. And now I'm going to click enter for my right bound. My guess, I got a pretty narrow window here, pretty narrow domain, so to speak. But you could back up a little bit too to get closer. It'll make it more efficient. All right, so now we have a y of 0. And look at this, it's no longer 181818. If we took the 5.181818, we wouldn't have the correct digits to get credit, right? We read the first 3 digits, and it would have been, you would have put down 1818, and it's really 1955223. So significantly different. So these are the digits we need. I'm actually going to take all of those. So we need, well, I guess I don't take all of them. I stopped at 2. Yeah, I stopped at the first 2. So that's the time we need. So we know that if we want to find the position of the particle, we're using that expression. It's basically the fundamental theorem of calculus rearranged, right? Where our final position equals our change plus our initial position. So kind of conceptually speaking, right? Where we end up is dependent upon where we started and how much we changed, right? That's the kind of the concept of rearranging the fundamental theorem. Okay, so we know our initial position is 2, so this is going to become a 2. We are finding this final position, which means we're finding the position at 5.19552. That's our final position. So let's take a look at that. What that means is that we started at 2, and this is all our displacement, right? That's all our displacement. So we can go from 0 to 5.9552 of our velocity function plus 2. So that's what we need to do. So I am not going to go back to my screen. I'll show you what I'm going to do here. I am going to do this. I'm calling an audible here because I was going to do it a different way. But I'm going to do a second calc integral 7, and I'm going to actually color this in. So my lower limit is going to be my x equals 0. And my upper limit is going to be my 5.19, it was 223. There is my change. It's 12.13477. When I add 2, I should get 14.13477. So 14.13477 rounds to 14.135. And that's your final position. Okay, when we get back into the classroom, we'll go through the takeaways pertaining to our motion problems.